Yes. The NQS, like it is. Otherwise, the NQS has.
I've been trying to persuade
the ones. Clear off his diagrams.
So I should let you know, I've been posting the videos up on YouTube. So if you go to the nuclear theory, the after nuclear theory YouTube page, all the videos are up there already so far. Okay, so our next speaker is Simon Sundberg from Ohio State University, and he'll talk about critical analysis of artificial neural networks in simple nuclear systems.
Thanks for the introduction, Dean. So I'm going to be talking about analyzing neural networks using techniques borrowed from quantum field theory, normalization group methods, and some Bayesian statistics. So, So just to start with, as we all know, otherwise we wouldn't be here, machine learning and artificial neural networks give us a lot of different tools and methods for analyzing nuclear systems, not only in new ways, but improving upon existing methods. And over at OSU, one of the things we're really interested in is understanding how neural networks work, and basically trying to open up this black box and understand what's going on in there. So in nuclear physics, we got a lot of different examples of applications. One of my favorite ones is this one where we're trying to extrapolate the values of no-core shell model observables for large model spaces by taking values from smaller model spaces as input and then getting this extrapolation going. We're gonna have a little bit more discussion of this later. But then there's also obviously these examples here with neural network quantum states, which we saw a couple talks about that before. There's a lot of involvement there. And then also just finding functional relationships between nuclear observables. So in this case, a really simple one, just using nucleon numbers, so neutron number and proton number to finding energy values. And I'm gonna be using this kind of as a test case to explore a bunch of ideas in this theory of neural networks. But yeah, the idea here is that we're gonna try to understand what's going on inside them and how to make them work better. So we want to understand neural networks. I'm just going to kind of review the basics really quick.
Ali, can you get this so it's not cut off?
Yeah, this is cutting off a little bit of important information down here.
Maybe the view. Point you try the views.
I tried different ones. This was the best.
Yes, sorry, but yeah.
Okay, cool. Now we can see my inputs, which is great because those are important.
And so see Dean.
Yeah. Hi, Dean. Hi, Dean. So anyhow.
I can make it large.
So we want to understand neural networks. So I'm going to just give a real basic review of what's going on with the neural network. We're trying to find a functional relationship between some input data and some output data. And the way a neural network does that is we feed some input up into the network where it gets scrambled by a matrix of random weights and carried to the first hidden layer. And in this hidden layer, all of these elements are called nodes, which just take our scrambled input plus a bias vector. And that becomes what's called a pre-activation Z, which gets acted on by an activation function. And this gets passed forward through all of the other layers in the same way until we get our output there up at the top. So basically all of that output is determined by all of these different random parameters scrambling things, but on a more macroscopic level from like the shape and architecture of the network, this is determined by what are called hyperparameters. So the depth and the width, so depth being the number of hidden layers, width being the number of nodes per hidden layer, and then also the activation function is considered a hyperparameter in this case. But right now, one thing to think about that's going to be important later is what does our function look like before we go and try to get a specific functional relationship? So what does our function look like now before we train it? It's just a random function that's being pulled from all these different random parameters. And if we were to initialize our network a bunch of times, we'd get different random function outputs. So basically, if we're going to initialize it, we're going to get a distribution of functions at the moment. That's going to be important later, but right now, we don't actually want a random function. We want a specific function. That's the whole point of this neural network. And so the way that we get that is we go back through the network and we adjust all of our parameters according to gradients of something called a loss function or a cost function. This just parameterizes the difference between whatever function we have and whatever function we want from data. So these gradients are going to end up depending not only on the activation function, but the other hyperparameters, and they also depend on the size of the output. And if we choose our hyperparameters poorly and we get these large or small outputs, what we end up getting is exploding or vanishing gradients, which just means that we can't actually converge to a minimum value in our loss, and so our networks don't actually learn. So practitioners will avoid this generally by adjusting hyperparameters until we get improved performance and stable training. And this works. We have a pretty good idea empirically of what things work in a neural network. But one thing that we'd like to know is can we improve upon this? And are there things that we're not considering? So this kind of motivates this idea of developing some sort of theory of how to look at these different neural networks. And so, right, we want this functional relationship. And importantly, the thing that we're going to look at here is basically trying to find not just a function that satisfies this, but a probability distribution of these functions. Because these parameters that we have, this theta star that I have up in the top left corner there, isn't necessarily unique. So if we can find a probability distribution looking at all of our functions, then basically we can find ways of quantifying error and knowing what exists in the landscape of solutions. So to start to get to this distribution, what we do is we look at the probability distributions that initialize our weights and biases, which in this case are mean zero Gaussians. And we can use those to calculate probability distributions for the outputs at any given layer in the neural network. And so the final layer is going to give us our random function output that we were talking about earlier. And one of the interesting things is that if we take the limit as the width in the hidden layers goes to infinity, then the central limit theorem starts to kick in on this sum. And what we're going to get is Gaussian distributions for all of our outputs in all the different layers. And more interestingly, if we back off this limit where we just have a large but finite network, we can start to look at these things as nearly Gaussian distributions that we can study as perturbations about a Gaussian. And then this kind of leads to an approach where if we want to look at our solutions here, we can kind of view them as a Taylor expansion about our initialization parameters. So all this talk of Gaussian distributions and distributions of functions should set off some bells reminding people of Gaussian processes. So I just want to cover those real quick, because what happens is in that infinite width limit, a neural network actually becomes a Gaussian process. And so one of the things that we want to look at for a Gaussian process is what it is. And the general idea is we have a joint Gaussian probability distribution that is specified by a covariance matrix. And for a set of inputs that we're going to end up trying to find some functional relationship eventually, this joint Gaussian probability distribution is going to draw outputs for all of our different inputs in this set. And that's going to give us a variety of different functions. And the idea is that we want a specific function, like we were talking about earlier. So we update the Gaussian process prior, this distribution of random functions, so that it reflects whatever data set we're trying to find this relationship with. And that gives us a Gaussian process prior, which then lets us find, a mean function that represents this functional relationship we're looking for, as well as error bars and uncertainty in the form of these standard deviation, these gray bars here. So this process is really dependent on that covariance matrix, since that specifies all of our distributions. And so how we get that covariance matrix is from a thing called a Gaussian process kernel, which is just a function that takes in inputs and then calculates the variance or covariance, depending on whether the inputs are the same or different. And that will let us determine properties like how smooth or how rough our functions are going to end up being, or if they're periodic in nature. The idea is we have a lot of different choices of Gaussian process kernel, and they'll give us whatever kind of fitting behaviors that we want to see. So going back to the neural networks and remembering that in this infinite width limit, they become Gaussian processes. There's a lot of analogy to explore there, and this also gives us some insight into the neural networks. So what I did to show that this happens in practice and not just in theory is I did a couple numerical experiments. I took a ReLU activation function, which is a very common activation function, and I took a neural network of a fixed depth, so 3 hidden layers, and then I initialized it a whole bunch of times to get a random distribution here. And what I find is that if I keep it at a very narrow width of 10 nodes per hidden layer, I get something that's not a very Gaussian distribution. But as I increase the width, it gets more Gaussian, and then eventually becomes basically Gaussian. So what we can, yeah.
Sorry, is it here the input is fixed?
Yes, the input is fixed. So in this case, I'm using I'm going to get into doing stuff with binding energy. The input is currently just for like iron 56. And so I'm just
I'm not saying the input is like a number, a single number, like 4.
No, so yeah, in this case, the input is N and Z for iron 56, and it's a fixed input. Yeah, so it's a 2-dimensional input in this case. Previously, I presented it with single inputs, but I'm doing this for a nuclear system, so I wanted to use a nuclear example for generating.
So you input say N and Z, and then it is fixed, say, and then this is just the output you get by randomly initializing your net 10,000 different, sorry, many times. So
500,000 in this case. Yep.
500,000 is just the width of the layer.
Right.
Okay, thanks.
Yep.
Is this just a manifestation of the central limit theorem, or is this something more subtle that?
No, in this case, it's just a manifestation of the central limit theorem. One of the things that's important, and this is kind of what the real point of the slide is, though, is that we have all of these different moments that contribute to our distribution when it's narrow, but as we get wider and the central limit theorem kicks in, the width ends up averaging out a lot of those statistical contributions until all we depend on is a mean and a variance. We only have a Gaussian distribution. So the idea is that as you increase the width, it's going to remove statistical correlations.
What can you tell in advance what the width and the mean is zero for this? Is this the mean zero always, or is this because of initialize the weights?
Because of my choice of initialization, I get mean zero in this case. Since I use mean zero Gaussians, all of my output distributions will also end up being mean zero.
The variance is also the one of the distribution you use to sample the weights, or?
Can you say again, sorry?
I mean, can you tell what the variance of the weight of this distribution is given the distribution of the weight?
Yeah. There are ways to analytically calculate that. Yep.
So it's very simple. You're scaling it by square root of n, so the width of this, so that they all come out the same, just like you always do in central limit theorem. Otherwise, it would be infinite.
Ironically, that's introduced basically to control the number of parameters and stuff like that. Like you introduce that when you're setting up these initializations, but it ends up letting us use central limit theorem very nicely and very cleanly. Yeah, Jane.
So here you've initialized according to Gaussians and you get a Gaussian as output.
Yes, when I get very, very wide.
So what happens if you initialize with small uniform? Do you still get a Gaussian or do you get a?
So you will. The reason I chose those Gaussians is that was an idea originally proposed by people that were developing this theory, but the nice thing about it is if you use Gaussians, it limits the moments of your distribution that you have in these narrower cases to only be even, and you have mean zero, which makes it so that if you were to do it with the uniform distribution, you would eventually get a Gaussian as you get wider, but it's not necessarily as clean in the intermediate steps, and you won't necessarily.
Maybe a simpler thing, you can do all the integrals.
Yes, that's what it eventually boils down to. Yeah, is you can do all the integrals versus the uniform distribution. Yeah. So, yes, Xilin, and then I really want to move on because I have tons of stuff to talk about.
Okay, so
yes.
the outing process is about a correlation kernel, right?
Yes.
So here, if you have two different inputs variables.
Next slide.
That's the next slide. Check this out. Wow. So basically, if we want, we can actually calculate the Gaussian process kernel. In this case, we have functions that are being drawn from this, and we have a probability distribution of these functions. And so what you can do is you can actually go and perform an integration and calculate this kernel, where we're just looking at the expectation value of the functional outputs. And so the ReLU activation function that I was showing earlier, if you end up calculating this kernel, it has this nice property where if the product of your inputs is positive, then these distributions are completely correlated. You can see that on the other parts of these corner plots here, where you have these just diagonal lines. And if the product of your inputs are negative, then they're completely uncorrelated. So this is just the form of the Gaussian process kernel that you get in the infinite width limit for the ReLU activation function. And I think this was James Halverson who did this, but he derived it for a variety of different cases. And there's more on this that I'll get to in the very next slide. But the general idea here is that I've got this at a width where the central limit theorem is starting to kick in, and we get these behaviors where it becomes a Gaussian process prior. And then I wanted to increase the depth to see what effect the depth has on it. And so what we can see is we go from one hidden layer to two. Previously, those distributions on those parts were uncorrelated, and we've introduced correlation. If I go deeper, they get more correlated. And if I get even deeper, they get even more correlated. So the thing that becomes important when we're trying to understand these distributions of functions so that we can go and do an analysis of what's going on with the neural networks is that the width, as we increase it, is going to average out correlations, and the depth is going to introduce correlations. And so the quantity that becomes really, really important to us is the ratio of depth to width, because it determines what's actually contributing in our probability distributions of functions. So another thing that's interesting is you can calculate these Gaussian process kernels, and you can also kind of reverse engineer it so that you can make an activation function that generates a particular Gaussian process kernel. This is supposed to be an RBF Gaussian process kernel, so radial basis function in the infinite width limit. And one thing that we found out was basically these correlations kind of match what you'd expect to see, but as you move to higher magnitudes of your input, they become less Gaussian. You can see they start to get the tail behavior isn't quite right. And so that shows that when you're considering these things, you have to worry about the size of your inputs when you're waiting for the central limit theorem to kick in. So more on this, I can answer more questions about this, but the general idea here though is beforehand, we're considering things in terms of what all the weights and biases we're doing. Now we're moving to a space where we're looking at functions as our degree of freedom, and we're looking at probability distributions for these guys. And so the next step is basically moving to a perspective where we're looking at things in terms of path integrals and calculating correlations and observables within the neural network. And so this gets back to this idea of saying, all right, we want to figure out what's going on with our solution function. And we wanted to try to Taylor expand about that. And that'll normally have, an infinite number of terms. But if we're using this approach where we have wide but finite neural networks, we can get nearly Gaussian distributions that we can treat using some perturbation theory techniques. And we can get an expansion in all the moments of those distributions that's controlled by this ratio of depth to width. And so we're only going to need a couple of terms. The people that originated this idea, Roberts and Aida, said you only need up to your second derivative. You only need like 3 terms. So with this in mind, we can basically calculate all these different distributions for the outputs at any given layer. And in the very first layer, it's going to be Gaussian. As you move forward in depth, it's going to become non-Gaussian, but we can calculate all of these different moments of our distributions just using Wick's theorem, since we have these nearly Gaussian distributions. So things start to look basically like doing quantum field theory with perturbation theory. And we can just calculate all the moments that we care about, like the 2-point correlator that's just looks exactly like we would see in a QFT class, with a 4-point correlator where we have a vertex contribution and then a bunch of 2-point correlators in products to give us this 4-point correlation. And when we go to infinite width, the vertex contribution that get calculated disappears, and some of the contributions for the product and 2-point moments disappear. And what we're left with is just 2-point correlators making up all of our 4-point ones. And this basically just gives us a Gaussian distribution, and the analogy that we can make is that this looks like a free field theory. So to really solidify this analogy to field theory, what we do is we say, okay, our probability distributions of outputs in any given layer are going to end up looking like some sort of exponentiated action. And that's going to have a Gaussian term, and then it's going to have a bunch of higher order contributions that are suppressed by powers of the width n here. And so like we have a 4-point interaction and then all these other higher ones that are suppressed. The other thing that is useful is if we look at all of these different moments in our distribution, they look like couplings in our action, and these couplings basically depend on recursion relations like this one below that act like a renormalization group flow with depth in the neural network. So what ends up becoming the name of the game here is we want to find fixed points in our coupling. We want to find values in these recursion relations that essentially make it so that they are fixed with depth. In particular, with the variance here, we want to do that because that'll determine the size of our outputs. If we think back, size of our outputs are going to help determine the size of our gradients. And so if we can have a stable output size, we can get a stable gradient and remove that issue from calculations. So to show this in practice, the ReLU activation function has a fixed point in its variance g, and that results from choosing our initialization widths for the Gaussians to be these values up here. These are the critical values for the initialization. And if we are above those values, we get it that our variance is going to explode. If we're below those values, it's going to vanish. And if we are at those values, we get a stable variance. And so this, again, is going to help mitigate any exploding or vanishing gradient issues when we're training. The other thing that's important is we go to the next moment in our distribution, since we're only keeping even ones around. If we look at the kurtosis, the 4-point interaction, this theory promises that if we're at criticality, the kurtosis is going to scale linearly with the ratio of depth to width. And if we're away from criticality, it's going to get very, very large, very, very fast. So we can see that again, if I'm above or below these values, I get an exploding kurtosis. But if I'm at criticality, I get something that's roughly linear. And the importance of this basically means that the kurtosis is the kurtosis is going to scale linearly with R, and higher order moments are going to scale with higher powers of R. And so this basically gives us a way to control what terms are contributing to our action. If we do this with another activation function, the soft plus, which is just a smoothed out ReLU, we still get this same limit with the central limit theorem kicking in. So we can apply this analysis again, where we go from non-Gaussian to Gaussian as we get wider. But unlike the ReLU, the soft plus doesn't actually have a fixed point in its variance. The variance is always going to be increasing or vanishing. And so this adds a reason why in practice, a lot of the time people say the ReLU does better than the soft plus, even though we'd expect a smoother function to work out. And if we look at the kurtosis, since there's no way to tune it to criticality, the kurtosis is always going to be exploding. We don't get that linear scaling, and so we don't have this kind of control over what moments in our distribution are contributing when we go to do these calculations. So all of this stuff so far has been for talking about initialization and architecture. Training is also a huge part of this because we're trying to get a specific functional relationship. I'm not going to go super in depth, but the training also has hyperparameters like the learning rates, and those can also be tuned to critical values. And the way that's done is instead of looking at statistical moments, we look at this quantity called the neural tangent kernel, which just determines how network outputs evolve during training. And if we look at its recursion relations with depth that it also has, we get prescriptions for how to scale our learning rates dependent on the width and the depth so that we can get stable training, even though we've introduced a new hyperparameter to our neural network system. So now that we have all these prescriptions in mind, the last thing that's kind of important is that this ratio of depth to width, like I was saying, controls what moments are contributing in the statistical distribution. And we can have different regimes basically of learning depending on how we set our ratio of depth to width when we're constructing the architecture. So the first one is this ratio where it's greater than or equal to 1. And the idea here is that all of our moments are contributing at values that are scaling with a factor that's greater than 1. So they're going to get very, very large, and all of our moments are going to contribute. So these figures here, I trained a neural network to learn binding energy as a function of neutron number and proton number. And what you can see is when I have it so that my ratio of depth to width is tuned to 1, I get the highest value of my root mean squared deviation over here on the left. And if I look at the actual residual plot, just taking the difference between my data and what my neural network learned, you can see that most of it is in the higher part of this color gradient. It didn't learn very many features whatsoever. If I go to the next regime though, and I make my network a little wider, we get to the point where it's effectively deep and can actually learn. And we can see compared to before, when I go now have 10 nodes in the hidden layers rather than 4, I get a lower value for my RMSD, and I actually get features that are being learned. If I make it even wider, I get better learning. And if I get even wider, we go into this final regime where the ratio of depth to width is starting to approach 0. And what you can see is beforehand, I had a lot of really well-learned dark features. There's a particular chunk right there in the higher end of the graph. But now those are less dark. It didn't learn those features quite as well. And so we're turning, when you go and get close to 0 with this ratio of depth to width, we're starting to lose our ability to learn specific features. So
did you try making the network deeper and wider, so keeping the ratio fixed, just increasing the number of parameters? And does it only depend on the ratio?
So no, it actually has, I meant to put in a slide about this, but the gist is that if you have a deeper network, it can actually learn features better. If you keep the ratio of depth to width fixed and say learn with one that has, say, 1 hidden layer versus a network that has 4 hidden layers, the network with 4 hidden layers will outperform the one with 1, even though the ratio of depth to width is fixed. Basically, this will let you control what you're working with when you're trying to perform these calculations. And so basically, even though you, sorry, my brain is shutting down a little bit here. Basically, the deeper network is still going to be able to learn these features better than the shallow network. It's just that by having a controlling scheme with the ratio of depth to width, you can make it so that it's not going to run the risk of exploding or vanishing as well. So all this to say, we have a lot of prescriptions, but the whole point of the last thing is that we want a ratio of depth to width when we're constructing neural networks that is greater than 0 and less than 1. because this lets us do this type of analysis to find critical values for the parameters that are relevant to us. And we want to choose activation functions where these critical points exist. And so after we have critical values for the initialization and the scaling, we can tune our networks this way to get the improved stability and performance that's offered. And so I did this with this binding energy case, but this was originally in a paper by Zhang and collaborators, and empirically they got similar results. It's important to note that their network has a small ratio of depth to width, and it has a tangent activation function in the hidden layers, which is something that can be tuned to criticality, but they didn't necessarily do. So I did a test case where I compared these different networks, some that were tuned to criticality and some that weren't, just to see what stability and improvements were offered. And so I used 3 different types of networks. I used one that was fully critical, where it's using a critical initialization and critical training. I used a half critical network, where it's just critical initialization. And then a fully non-critical network that's just using the standard out-of-the-box versions of things from PyTorch. And I performed this with ReLU and Tanch, and I used a stochastic gradient descent optimizer because all of these things have prescriptions for tuning to criticality. Then I also did some fits with the adaptive optimizers, so like Atom and RMS prop, but those currently don't have a critical prescription. So the important thing to see here is that when we use a mean absolute error loss function, like they did in this paper, the fully critical network, which is the blue line in all of these plots here, outperforms the other ones for all depths. And networks that have criticality, so the blue and the red lines as we go and increase the depth, are getting loss values that are orders of magnitude lower than the fully non-critical network. And so this offers some improvement when we're operating with a ReLU activation function that has critical features introduced. If we do the same analysis with Tanch, it's a little messier, but for all cases except for the very shallowest one, we end up getting the fully critical network outperforming in all cases. And we can also see that as we get deeper, so this is similar to what we were talking about before, where a shallower one with the same ratio of depth width might do worse. As we get deeper, it's able to get a better loss value for both of the critical networks, whereas the non-critical one seems to stagnate after about 2 hidden layers. So to check even more about the performance here, I calculated the root mean squared deviation for the data set. And for the fully non-critical network, I get an RMSD of about 8.35 MeV, and the best value that we got is down there circled in red. When I go to the half critical case, I get an improvement to 2.23 MeV, so by about a factor of 4. And there's that best value there at about a depth of 6. And then with the fully critical network, I get the best result of all. So this seems to continue to indicate that these critical networks outperform the non-critical cases. So lastly, I did things with the adaptive optimizer where I use this instead of stochastic gradient descent, which has a fixed learning rate. And I used a critical and non-critically initialized network to see what RMSD values I got. And they ended up getting pretty similar values to what Zhang proposed. But if we think back, the fully critical network with the non-adaptive optimizer got a value that's not as good as these, but is still comparable. And so this seems to suggest that the adaptive optimizers might be compensating or hiding features that we might want to look into. So just to summarize, neural network, field theory, neural network criticality, this offers a way of understanding what neural networks are doing, and it gives us prescriptions for how to set up the architecture and training of a network. And then we can see that these critically tuned networks outperform the non-critical equivalents in this test case for binding energy with a stochastic gradient descent optimizer. And then the critically tuned networks are going to be outperformed by the adaptive optimizers, but for the fully critical case, it's comparable and they differ by a much smaller factor than the non-critical case with the non-adaptive optimizer. So some things to look into. I want to continue poking at binding energy with more. Oh, yes, Jane. Oh, so yeah, okay, sorry. So we want to add more features to the binding energy, include pairing effects and shell closures, and see what happens there and see if this performance still holds up. And we want to extend criticality to those adaptive optimizers and to other activation functions, and check out more nuclear systems, either ones that are well understood to see what's going on with learning behavior, or see if there's improvements that can be offered to existing systems that use neural networks. And then lastly, just extending this field theory ideas beyond just using perturbation theory as an analysis tool. And then, yeah, just looking at other ways of getting central limit theorem violations that might offer us new ways of looking into this. And last quick advertisement, I promise. I was talking about this extrapolation case where we're trying to extrapolate no-core shell model observables, and Sunil and Tom, who are members of the band collaboration, are currently trying to duplicate these neural network results using Gaussian processes. And they're doing that where it's aware basically of this kind of convergent behavior. And they're trying to see what's going on there and offer ways to see how the neural networks are learning through comparison. And then hopefully I can come back in with an infinite width neural network and offer some comparison there, and we can see if we can learn more about how things are learning. So here's some resources, but otherwise, thank you for your time.
If
Yeah.
an activation function having a critical point has something to do with whether it's exactly zero somewhere.
It does actually. I would have to look this up, but in, see, actually I have my resources right here. So this Principles of Deep Learning Theory book discusses this in chapter 5. They discuss different features of criticality, and they.
So for your soft plot function, if you shifted it just a tiny bit down so that it crosses zero, would it then have a critical?
As far as I remember, no, because there's two conditions. One basically saying that yes, if you shift it, so for certain activation functions that meet criticality criteria, it will actually make it so that it does have a critical point. But there's also a second condition relating to the derivatives, and I think the soft plus doesn't actually satisfy that condition. So you can shift it, but I think something about the nature of the derivatives of the soft plus makes it so that it still does not have a critical point.
That's later.
Yeah, I'll pull up the book and we can look at it in a minute too. So.
Patrick.
So how do you separate the effects from, so as you're increasing this width and you're looking at, there's this critical point. How do you separate that effect from the transition from an overdetermined to an underdetermined problem? You do around the same point, actually, I did some napkin math for at least one of your figures. You do switch between those two regimes.
So when you're saying overdetermined, you're talking about in terms of the number of parameters in the network?
Yeah, and the amount of data you have.
Right. Let me see. I think I have a figure about this. So there's in this work here, there's a discussion essentially that at a certain point with neural networks, if they get large enough, you'll have some sort of overfitting and overparameterization, but eventually at a certain size, they kind of switch back over. And the way I kind of tend to connect this to the theory and the way that Roberts and those guys do as well is basically by saying that beforehand, you're considering things in terms of the parameters that exist within the network. But now we're considering things where our degrees of freedom that are relevant and are determining what's going on are like the statistical moments of this distribution, the neural tangent kernel, and the functions. And so the idea there is like, eventually you get this benign overfitting. But the idea is that maybe that's explained by us going to this limit where we care about these degrees of freedom rather than caring about every single weight and every single bias. So more to look into there for sure, but that's kind of the explanation that I've thought about and the explanation that's been offered to me by other people doing this.
Was this your very next slide after your references?
No, it was this one, and then this one. So this was recycled from a talk Dick did at Darmstadt, and then I made that thing talking about the different regimes and moved this back here, just in case I wanted it. But no, but conveniently this happens to be there, so that's nice. Yeah.
But you did not pay me to ask that question.
It is a really important point that the degrees of freedom are not what you think they are once it gets big.
This is separate from regularization. That doesn't change this.
That's right. This sort of regularizes by the central limit theorem, right? It averages out stuff.
Other questions? So when you show the performances,
Yes.
With respect to the mass,
Yeah, the loss values.
the loss values, these are during training, I guess, right?
Yes, they are.
Like testing and validation, do they all decrease or not?
Yes, they all decrease. I'd have to look at the specific values that I had, but yes, they're all.
There's no overfitting here. So.
There's no, yeah, that was a question that was asked at ABS actually, and yeah, no, there's no overfitting here.
Thanks.
Okay, let's thank Simon once again. Our next speaker is Daniel Lake from MSU, and he'll talk about accelerating DFT simulations for uncertainty quantification in nuclear structure.
Great, thanks for the introduction. Thank you all for being here. As Dean said, I'm going to talk about some of my work accelerating DFT simulations. I'm going to start with a little bit of background, what we're trying to do, and some of the stuff that's already been done. And then I'm going to really dig into the nitty-gritty, which essentially the problems that we have related to the self-consistent problems we're trying to solve. For ease of understanding, of course, I'll start with a toy model. It's going to be a modified version of the Gress-Pijewski that Patrick talked about earlier. Then I'll go to real HFP theory and spend the remaining time talking about some initial applications. And just like the rest of the day, feel free to interrupt me if you have any questions along the way. So we do density functional theory, and this is motivated essentially by the success of the independent particle picture. So you imagine you have some mean field Hamiltonian, you have some single particle levels, and you fill it up with protons and neutrons. The key point when we do HFB is we say that the mean field is generated by the other nucleons. So a proton on the left side of the nucleus moves in a mean field generated by the rest of the nucleons. And it generates a mean field that helps determine the motion of, say, a neutron on the right side. In practice, we work using the pairing at the HFB level, and that means that we're doing the variational principle with a generalized Slater determinant as our trial wave function. But this doesn't end up looking too complicated. You end up solving something that looks an awful lot like the Schrodinger equation, just using a density-dependent HFB matrix. So you have your HFB matrix H, and you diagonalize it looking for the eigenvalues and eigenvectors. And the complication is simply that the HFB matrix depends on all of these wave functions. The way we come up with this matrix is we actually write down the total energy of the system. Used to be you would write down a many-body interaction. People have moved away from that in the past couple of decades. We write down the total energy as a functional of the local densities and currents, and we call this the energy density functional. Then we vary that total energy to derive our HFB matrix. And one of the key points here is that this is fairly divorced from an actual many-body interaction. What that means is we actually, like the form of the EDF may be inspired from physical motivations, but then we actually have to fit the EDF parameters to some choice of data. So then, as we'll come back to later, one of the things we would like to do is propagate the uncertainties from our calibration through to the things they compute. The first question is what we actually want to compute here. The thing I'm interested in with density functional theory is fission. I'm not going to spend too much time describing what we want to do with fission calculations. Suffice to say that for every nucleus for which we want to compute fission observables, we have to carry out a whole bunch of constrained DFT calculations. So you see you have a grid here in 2 collective coordinates, and for every grid point there, you do a constrained HFP calculation. If you imagine fission as tunneling through an effective barrier, this is how you get that barrier. So for every nucleus you care about, you're doing hundreds or thousands of DFT calculations. And we care about a lot of nuclei. If you're interested in our process nucleosynthesis, the different nuclei that you care about, well, it varies a little bit based on which model you use, but you see that abundances of nuclei that are relevant, there's a couple hundred of them that you would have to do calculations for. And then on top of that, you're not always just interested in spontaneous fission. Induced fission plays an important role as well. And then you can imagine that as another coordinate you have to scan over. So for these things, you're doing an awful lot of HFB calculations. So we have turned to emulators in the past. We're continuing to develop them. What I talked about last year is a work just using neural networks to emulate the potential energy surface across this R process region of the nuclear chart. And the gist of that story is that the neural networks work reasonably well. What I show here on the left is that effective barrier for one nucleus. And on the right, I show the difference between that barrier using the real calculations and using the neural network emulator. And this gray region here is the region relevant for the fission calculations. You see that the difference is fairly small, 500 keV and MeV or so, and that seems reasonable. When you then propagate that uncertainty to something like the half-life, you again see that the neural network is doing reasonably well. Here I plot for you the DFT half-life on the x-axis and the neural network half-life on the y-axis. And you see that the neural network agrees within an order of magnitude or so, especially within this inset region here, which is relevant for our process nucleosynthesis. So that's sort of where we left the story last year. But there are other things we can do. One of the things that we would like to do is make these predictions with quantified statistical uncertainties. This is especially important for when you're looking at fission rates far from stability. And this has been done for individual nuclei. What I show here is the one-dimensional barrier for plutonium-240 with a gray band indicating the propagated statistical uncertainties. And if you look at these numbers here, they're about plus or minus 1 MeV. That's just from the statistical uncertainty. That number is similar in scale to the emulator error from the neural networks I was just talking about. What this means is that if you use that sort of neural network emulator to try and propagate statistical uncertainties, you expect to overestimate your uncertainty in the predictions you're making in a rather drastic way. So what I'm actually going to talk to you about today is a different class of emulators. You've seen a lot of things that you might consider intrusive emulators, and I'm going to talk you through just a little bit of background on how to understand them and some of the subtleties that we have to approach with our DFT calculations. So one way to understand the sorts of emulators we are thinking about is as projection-based emulators. You can imagine solving your HFB equations as solving equations of motion in a very high dimensional space. What you find with similar calculations is that the motion actually takes place in a low dimensional submanifold of this high dimensional space. So in this figure here, maybe you're solving this parametric eigenvalue problem, and you're solving it in a 3-component wave function, but perhaps the wave function really only varies within this gray plane here. This is especially common when you're doing things like uncertainty quantification, uncertainty propagation, where you're repeating calculations in a well-constrained parameter region. And so the goal then is to solve your equations of motion entirely on this low dimensional manifold. And because you're working in this reduced space, you expect to be able to solve your equations with small error considerably faster than in the real space. There's a couple of recent reviews I'll refer you to here. There's also a number of textbooks that discuss related problems. Perhaps the one I'm at least most familiar with is what we call the reduced basis method. It's very closely related to eigenvector continuation. So suppose for a second that you had an analytic Hamiltonian that you wanted to diagonalize. It could be something simple. It could be a harmonic oscillator or Wood-Saxon. You can sort of make it arbitrarily complicated. Now suppose that all you care about is the ground state, or perhaps the ground state in the first excited state. Then it seems reasonable to work using the wave function degrees of freedom. You just make your Hamiltonian, diagonalize it, find your eigenvectors, and you're done. What the reduced basis method does is it says I'm going to build a tailored basis for each wave function that I care about. And we typically do this using the singular value decomposition. People have also called it today proper orthogonal decomposition, etc. And then you project the Hamiltonian into that reduced basis. Then your diagonalization problem is computationally inexpensive, and you get the results that you're after. And this has been applied widely in nuclear physics over the past couple of years. There's a couple of works I'd like to highlight here, showing that this works even when you're solving a self-consistent problem. And if you're interested in learning some of the basics, I will also refer you to this neat guide here. It's maybe a couple of years old now at this point, but it still serves its purpose. So the problem we want to solve is this self-consistent one. And before I get there, I want to point out a subtlety to you. Suppose you're interested in solving a problem with just this Wood-Saxon potential here. The parameter you care about is this alpha parameter here, and it appears in a non-affine way. If I want to solve this in a basis expansion method, it doesn't matter whether I'm using a harmonic oscillator basis or a reduced basis. I can't pre-compute this transformation as I vary alpha. While the reduced basis method still provides a speed up over a generic basis, this non-affine parameter dependence drastically reduces that the utility. Empirical interpolation solves this by approximating this potential. You split it up into a bunch of terms that depend only on your interaction parameter alpha, and a bunch of things that only depend on your coordinate mesh x. To evaluate these parameters, these expansion coefficients b, you can do that by just evaluating the real potential on some subset of your grid, and then solving a matrix problem for the expansion coefficients. Then, with this empirical interpolation in mind, you can pre-compute your Hamiltonian in any basis that you want. And when you combine this with the reduced basis method, you see further speedups. One thing I'd like to point out here, it took me a while to wrap my head around this as well, this can still be understood as a projection-based emulator. It's not a projection-based emulator in the wave function sense. But if you imagine your potential lives in some high-dimensional space, you are still projecting it down into a low-dimensional place. And so a lot of the machinery and a lot of the intuition that comes from using the reduced basis method still applies. In particular, some of the accuracy that we'll see later really shouldn't come as much of a surprise. So that's if you have something like a Wood-Saxon potential. What happens when you have a self-consistent problem? And I'm going to show off here just a modification of the Gross-Piotrowski equation here. I want to focus on this self-consistent potential here. We already saw this with sigma equals 2. In practice, we actually let this sigma value vary, and that is how we get improved performance in the like a Skyrm energy density functional. So some of the things that like Patrick was showing earlier have reduced utility. In particular, you can't pre-compute this potential in whatever basis you want because you're going to be varying the exponential power as you go. We would like to solve this again by using this empirical interpolation that I just showed. And there are essentially two steps. The first is you have to find those basis functions to expand this field, and then you have to evaluate the expansion coefficients. The first one pulls straight from the reduced basis method ideas. You generate a bunch of sample fields, examples are shown here, and then you take the singular value decomposition of it, and that generates your basis fields informed by the samples. In general, you don't need a whole lot of them. If you want 10 to the minus 4 relative accuracy, in this case, maybe you only need 10 basis fields. But that field is not given in a closed form. So in order to evaluate those expansion coefficients, I have to detour a little bit to explain how we actually solve self-consistent problems. It's actually deceptively simple. You start with an initial guess for your density, and then you construct your Hamiltonian. You diagonalize it, and then recompute the density. And then plug that back in and regenerate a new Hamiltonian, and you repeat until the density that you put in is equal to the density that you get out. And there's a little bit of special sauce that goes into this, but this is the gist of it. What you can do is you can actually apply this same iterative scheme to your expansion coefficients. You start with some initial guess for the expansion coefficients, make your approximate Hamiltonian, diagonalize it, and recompute those expansion coefficients using the density and the wave functions from your diagonalization. And then you repeat this until the expansion coefficients converge. So then you can do that. And when we look at the toy model, this Gross-Piotrowski, I can show you again another cat plot like we've seen earlier. You can look at the total runtime versus the root mean squared error on the eigenvalues. And you can compare against just a harmonic oscillator basis expansion shown in these blue X's here. You see, first of all, as you increase the number of basis states, your error drops to 0. That's as you expect. As you increase the number of basis fields, you say following these green triangles here, you move from top left to bottom right. The total runtime increases and the total accuracy increases as well. One way to understand this is that the number of basis fields which roughly corresponds to the amount of training data that you need to, the number of real calculations that you need to do to get things to work. And you see that there's a nice, neat 100 times speed up just using empirical interpolation, still in the harmonic oscillator basis. When you then use a reduced basis on top of that, as shown in orange here, you get an additional factor speed up. So this sort of thing works for self-consistent problems. One thing you might be concerned about is what happens when you increase the number of wave functions you're trying to track. So in the top panel here, you see the case with 5 wave functions you care about. In the bottom, you see it with 20. And while you still see the drastic speed up between empirical interpolation and the harmonic oscillator basis expansion, that speed up is drastically reduced as you increase the number of wave functions. The way we handle it is something that's necessary for the HFP case. I won't dwell on the specifics of this here. Suffice to say that eventually you end up with a reduced basis that's similar to the original basis that you were working with. Your tailored basis is about the same size as the harmonic oscillator basis, and there's no speed up to be gained. So that's the toy model. And now we can get into HFP theory. So to set the stage a little bit, about a decade ago, there was a good bit of work done by the unit of calibration to calibrate a series of SCRM energy density functionals such that they have posterior parameter distributions. There, they ended up using Gaussian process emulation techniques to really explore the landscape. And you can see the posterior distributions shown in this figure here. What I did was I took 1,000 samples from this posterior distribution and used it to apply this empirical interpolation approach to a number of different nuclei and a number of different test cases. And I'll point out for most of the tests that follow, I'm only using 100 data points as training with 900 as validation. Strictly, we probably don't even need 100. As we'll see, you can actually go quite a bit more. So the first major difference between HFB theory and our toy model is the number of different fields you have. You have a number of different local densities and currents. You have your particle density rho, you have your kinetic energy density tau, you have this rho tilde, which is the pairing field, you have the spin orbit, and so on. Depending on what appears in your EDF, you may have more or less of these. And you have one each for protons and neutrons. So then you need to do this empirical interpolation for each field individually, meaning that you take the SVD of each field individually. And you can see that depending on the object you're considering, you need more or less basis functions. For the kinetic energy, for instance, you can get away with as few as 10 basis functions. For the pairing field, you need 70, 75 or so. And it's really this maximum number that tells you how many HFB calculations do I need to generate the basis that I care about. You can take a look at these basis fields and you'll find that they're not shocking. They're maybe not like the most clear if you don't work with these objects day in after day. But for instance, in panel A here, I show just a sample field. That's fine. And when you look at the most important basis expansion field, you see that it's essentially the same thing. It's just up to a rescaling. Okay. Then the next few basis fields, they're surface peaked. They're all still localized around where the nucleus is. They just contribute much less to the basis expansion. So you can see pretty clearly what's happening. As an example, because the nucleus is always compact in this region here, you'll never see a basis field that's non-zero far out here. So then we make these basis fields and we apply it, and the first thing you ask is, does it work? The answer is yes. What I'm showing here is the error in the binding energy in MEV versus the required number of training points here. And what you can see if you just look at this blue curve here is that the binding energy error drops off dramatically. It's down here, down to tens of electron volts. You can really get it just to be as small as you would like, provided you're willing to do more HFB calculations to get the required training data. This is far below both the neural network emulation error from before. It's also actually below the error from the harmonic oscillator basis truncation. So you wouldn't expect a number out here to really describe the physics to within tens of electron volts because your EDF doesn't describe anything that precisely. If you want to be more realistic, if you want a mere kilo-electron volt root mean squared error, you see that you only need as many as 30 or so real HFP calculations to get the emulator to work. And that's really nice. It means one of the goals you would like to see is do as few HFP calculations as possible to then develop your emulator. And then we can ask, of course, is it faster? Does it help? If it's not faster, why am I doing this at all? And again, the short answer is yes, it's faster. What I plot here is the runtime per iteration versus, again, the binding energy error here. And if you just look at these green squares versus this red line here, you see that it's about an order of magnitude speed up. One thing I'll point out is that the runtime per iteration doesn't drastically change with the reduced basis time. And that's because you're bumping up against the diagonalization time. Now the diagonalization time is the bottleneck, and you would have to approach that to see further speed. I'll also point out that the emulator is written in Python, and I'm benchmarking here against the Fortran code HFP-THO. You see that as an additional factor speed up when I compare to an equivalent HFP solver written in Python. So we come back to the wave functions. And unfortunately, what we'll see is that there's very little that we can do. The first issue is that when you break the symmetries, you have a lot more wave functions you have to keep track of. Think about axial symmetry versus spherical. And in this case, we break parity symmetry. But it gets worse. We're doing HFP theory. We're including pairing effects. And that means that the states are partially occupied. So what you see like an occupation distribution that looks a little bit like this. So even when you're well above the Fermi energy, a lot of the wave functions still contribute and you have to keep track of them. So this means you actually have more quasi-particle wave functions you need to track than you have number of nucleons in your system. And there's also a subtlety with level crossings that makes some of these problems less tractable. And what we find is that that issue we had earlier in the toy case when we looked at the reduced basis method gets even worse. In many cases, it actually makes the emulation totally unusable. Your error is just MEV, tens of MEV, and that's, yeah, Xilin.
So how many levels do you actually have in the realistic calculations?
Yeah. So because we have axial symmetry, the largest block ends up being about 300 states. You probably only need 100 of those, maybe 150 of those to capture all the effects you want. But then that's 150 like of the lowest neutron block. And then you've got that same number again for the protons. And then you have L equals 1, L equals 2, L equals 3, all the way up.
When you say the cost of diagonalization, is that about that? Like you have 300 levels?
So we end up with the same size HFP matrix that we're diagonalizing, regardless of the number of basis fields for our empirical interpolation. And that number is, in practice, the largest block is 700 by 700 because you have the positive quasi-particle energy and negative quasi-particle energy as well. It's not a large matrix. It's not the largest, not by a long shot, but it is the computational bottleneck in our approach.
Because you have to iterate it many times.
Yes, yeah, thank you for bringing that up. Again, this is still an iterative method. So we're still solving the HFP equations. So it's not just diagonalizing that matrix once, it's diagonalizing it again and again and again until you have reached some convergence tolerance. Yeah, thanks for bringing that up. That's an excellent point. So we've applied this approach in a number of tests, and essentially the results are pretty similar for the different tests. We've looked at varying the number of major oscillator shells. We're looking at medium and light mass nuclei. The results I was showing before were for fermium-254. We've looked at actinide region as well. We've done this working with approximate particle number restoration, and the results are all pretty similar. I'm not going to go through all or really any of those cases because it's just sort of showing a cat plot that's the same every time. So the sort of neat bit here is that, again, this is a projection-based emulator. So you expect it to extrapolate about as well as, say, the reduced basis method. And so what I did here was I said, I'm going to take some 50 data points closest to our median parameter, use those to inform my empirical interpolation basis fields, and then just do empirical interpolation, extrapolating far out in my parameter space. I only show 2 parameters here because I've made the 12-dimensional corner plot and it's totally unreadable. What you can see is that the emulator extrapolates essentially near perfectly across this realistic posterior distribution. So anywhere within this flat curve here, it's interpolating. Anywhere outside, it's extrapolating. And the left panel here is 10 to the minus 6 basis truncation threshold. The right panel here is 10 to the minus 3. And you see that it's performing as expected. I should clarify, this is the binding energy error on a log scale again. So here we're sitting down at tens or hundreds of electron volts. Now we're back up to keV or tens of keV. And this is the realistic posterior distribution range. So, I mean, yeah, it's able to extrapolate. And again, this sort of shouldn't really be a surprise. The last thing I want to point out is that this is useful for some of the downstream applications as well. We've done tests with fission isomers for actinides. For anybody who's unfamiliar, if you look at a fission barrier, the fission isomer is this minimum here. It's some deformed state that the nucleus will tunnel through as it's undergoing the fission process. And there are properties you get out of this that you get for free. You get, for instance, the deformation, you get the excitation energy over the ground state, because again, you're really solving the HFB equations. So you get out your wave functions and you get out your densities at the tail end. Similarly, there are other quantities we use to compute fission observables. The localization functional here, you can take a look at the expression in this paper here. We use it to compute fission fragment yields once we exit the tunneling region. And if you just look at the left panel and the right panel, you see that they're indistinguishable. Again, we get this for free in our emulator because we are genuinely solving the HFB equations. Contrast with something like the neural network I showed at the beginning, you would then have, if you took that neural network emulator, you would have to go then do a real HFB calculation at the tail end. So just some conclusions to wrap it up here. What we've seen is that we get an order of magnitude speed up in real DFT calculations with arbitrarily small errors, and we don't need a lot of training data to do. There's a lot of future directions to take this work. As Xilin pointed out, one of the things we would like to do is move away from an iterative solver. If we could come up with the HFB matrix at convergence and then just diagonalize that once, that would be an enormous speed up. There are lots of approaches that could get that to work. One of the things I'm interested in is approximate orbital-free EDFs, where you never touch the wave functions ever. And then, of course, on the physics side, there's all the applications I mentioned at the beginning that I would like to just take this and run with. I'll thank my collaborators. Thank you all for your attention and open the floor for questions.
Nice progress. Other questions?
It's not a question, I just wanted to defend my method from your vicious attack. So since the slides are on the Google Drive, the second reference in my talk of 2 references is a paper where they talk about how you can take any nonlinearity through just a couple auxiliary variables, turn it into something that can be projected using stuff.
I'll have to take a look at that.
Also, DIM or DI,
Yeah.
you can just bake that in. You can make that your onsides for the PMM as well, right? You can
Yes, yes, you're right.
equation
You could-
free.
I'm going to bother you when we get back, because that's
No,
probably
no,
the Please. Okay, yeah, thank you for that.
Supposed to write it.
Okay. Other questions? So actually now going to this road to the sigma power, so what values of sigmas do you end up getting?
So when you're looking at the real skirm EDF, you have a row, they parameterize it as rho to the 2 plus alpha. And there alpha hovers between like 0.5 and 1. So like previously I've talked with Patrick, we've had some ideas about like some Taylor expansion or something around alpha equals 0. Eventually, what you find is that you need too many terms to really get any benefit from that approximation.
But is there some physical meaning to that? What?
Yeah, so I don't know that there's much of a physical meaning to the value of that parameter. That term itself originated as the three-body contact term. And historically, what was found was that letting that power be a fit parameter improved the results on things like the binding. Yeah.
Questions? Well, let's thank Danny once again.
Oh, yeah.
Oh, so
It's online?
It's online.
Okay, sorry. I was thought like fairly. Yes. Don't use that. Viruses. Yeah. I actually.
There's some certain activation agents. There are like contributions to higher order moments that cause.
No,
That's
there are
these three. Stuff like that.
I'm not sure. I'm actually. Yeah.
I think if you click on the picture of Dean,
Yeah,
and then hit the bottom right one, right?
Yeah.
There he is.
it's impossible to use. All right. Okay.
Video game.
Oh, yeah.
That's that one.
Why is this
Worst video game ever.
really terrible?
What's going on? Your cursor control is.
It's a little.
We have time.
No, don't download it. Sorry, this is twice way.
Huh? Does it work?
Yeah, very
Online?
good. Understood.
Just,
Yeah, very good.
Maybe you're rolled over, right?
Oh, maybe is it?
That's the
Oh, okay. It works, that's the thing, I mean, it is. No, use it for the. No, some more. Just want to reduce this. Oh, thanks. It's really, don't move. If you move.
Oh, if I move that, you will
Yes,
move.
no, you're, yes, this blackboard and you. Okay, wait. Very good.
All right, our next speaker is Zhang from FMSU. And he'll talk about update on the emulators for nuclear continuum physics.
Okay, so I'm going to talk about continuum emulations. And just let you know, like there'll be like 2 different talks tomorrow, also about continuum physics. Outline update on the 3 nucleon scattering, real energy emulators. Then I would like to have more discussions on complex energy one, because I sense that I would like to explain more details to get our discussion going. And then the other one is about NQS for continuum. And I will end with some, and also some discussion points. I would like people to address them in this meeting here. So quick update on NDs. So we're looking at proton deuterium scattering below deuterium breakup threshold. The goal is to use that eventually calibrate functions using Bayesian analysis. Of course, looking into the even further future, you could apply this kind of framework to think about neutron nucleus scatterings would be relevant to isotope studies. So it involves people from our collaborations and also the group that we have been working on the field body continuum for a long time. So some results, I believe, last time in the last meeting, I didn't show this result because we didn't have them. So this is about thinking about three body interactions, two parameters, CD and CEs, and okay, so then the plot is about a particular energy, 0.2 MeV, and then for this particular 1/2 plus channels, there are two different waves. Yes, S wave and D wave. So then there's 4 different numbers to characterize the reaction amplitudes, R00, R01, and R11 here. So then yes, this energy 0.2 MeV, and this one is closer to the breakout threshold. So the show is the log 10 of the errors here. And then there's like 5 training points on the corners and in the center. Okay, so the tiny errors with 5 training points, and then you look at how the errors or the mean error change with energies. That's to give you a feeling about how the performance of emulators. So these are still preliminary results, and then so by the way, so there's a new paper also come from our collaborations involving Christian, Dick, and Christian's previous student. The paper nicely the greedy algorithm in this proton neutron scattering emulation. So this still like the very preliminary results. This is about now we have a faster way emulate the errors or to estimate the errors of emulations in this parameter space. Okay, so you may be able to see that the pattern is similar to the errors I showed before. Okay, the idea is then that based on the fast estimation of errors, this will tell us the next step to put the training points. So the goal is to save the cost for the training calculations. So there is this very nice workflow there you can find in the paper. I don't think I need to go through that here. You want to tinker with it? Okay, thank you. Yeah, so that's the current status of this. So hopefully we can get these wrapped up soon and get them posted online. Now I want to, yeah.
No, you broke.
What? Unless I, if you click it, yeah. Okay. So yes, so I want to spend a bit of time on this because there's some interesting things I will share with you and to see whether there's some potential new ideas come out by discussions. So the idea was this, right? To think about the Schrodinger equations in an inhomogeneous form, basically trying to solve this problem using Green's function method, and think about complex energy plane as a parameter space, and then think about doing training calculations in that blue colored region, and then think about how to do extrapolation down to the real axis by using emulator technology, right? So during this process, so basically the papers are out. They were out last year. They're being reviewed right now. And during that process, as people already mentioned, this is essentially a projection method, the subspace projection method. So you can ask, okay, how does my Hamiltonian look like in that subspace? So if you look at this expression, right? So this expression about resolvent or Green's function and matrix element between two different sources, And it's also overlap between the one source and your solutions of that inhomogeneous equations. So for example, if you look at response functions, the source are localized. So basically the ground state and multiply or applied by a excitation operators, like electromagnetic operators. So it's a localized object. And so this is why the solutions that the part of the wave function that is really relevant for this quantity is an internal wave function. Okay, and this is important because at a complex energy, the solution are all localized. So then the extrapolated wave functions also localized, meaning that they don't have the right asymptotics, but it has the right internal wave function. And that's the important thing here. So, and then the other thing I want to say is that if you think about the spectral decomposition of this quantity, right? So Hamiltonian is a matrix. So this quantity as a function of energy, basically the sum of poles. So it's very important to keep this in mind that when we talk about spectrums and when we talk about continuum physics, spectrum will give you, or the eigenenergy give you the pole locations. Okay, this is true for any general framework doing finite matrix calculation for continuum. So this is important because I'm going to talk about, what does Hamiltonian look like in the subspace? That tells you where the poles are in these emulations. Of course, so that's about energies. So you can think about emulation for theta in the same way. Just increase your dimension parameter space. So actually, so in the paper I already mentioned that this is the introductory, like the method, the idea is very similar to this so-called rational Krylov subspace method. So the idea is a typical method, like power method, is you apply your Hamiltonian of some matrix or some vector again and again, and that helps you to find a good subspace for your problem. But the rational approximation, basically, you apply this resolvent, like 1 over E minus H, if you think of sigma as your energy variables, and you have a bunch of different sigmas, and that gives you a subspace, right? So this is called rational Krylov method. So it turns out like, so I bring this up because this morning we have Lauren, Pablo, and the group talking about PMM for the response function calculations. So even though it's a PMM, but the idea of using small matrix subspace is very similar. So in the quantum chemistry, I think it is quantum chemistry. There's 2 papers I'm well of using similar ideas. So basically, find a Hamiltonian and you do dimensional reductions, but then you still get the essential spectrum, right? But then you notice that there are discrete levels because they try to keep the structure of Hamiltonian the same as the original Hamiltonian. And in the HFB, I believe the eigenvalues are all real. So the poles are on this line, on the real axis. So and by the way, the one paper is actually carbon cluster, the other one is DFT. And the other interesting thing is that they are the members of your nuclei collaboration. Okay, so it's worth talking to them about this. So so this is about PMN. Think about response function and parameter dependence. So I think Nambu gave a talk on nuclei maybe like 2 or 1 year ago about the energy variation for emulation for the response functions.
Yeah. So at least in the tensor network community, the emerging community, what people try to do is always to use the standard, because applying e to the minus sigma I to the minus 1 is hard.
It's expensive.
It's very expensive. Yeah. I mean, the first line is way cheaper than the second. And in fact, what they typically do, they try to expand A minus sigma 1I or something in terms of A square A cube, just because it is very hard. So when, I guess in Kaur cluster, the midfield theory, you can actually reorganize this, how the inverse of this operator in an efficient way.
They have some
But
way.
generally, that's not true, right?
It's not easy. It's not trivial. But the purpose here is that to use this parameter to enhance part of a spectrum that you want to get.
Oh yeah, no, that, I mean, if you could do the second, it's clearly way more powerful, right? Because there's a resolution in a sense. Yeah, but I just want to point out that typically it's way more complicated to do.
I agree. So the problem is this, so if you keep the Hamiltonian still like a subspace Hermitian, or in some way that even though it's not Hermitian, but the eigenvalue is still real. So you get this type of problem that you still have the poles along the real axis for response function. So if you look at this is a toy system, you can think about this as a response function or some functions like these, function of energies. You can see like if you keep things Hermitian, this guy, you will have poles. So this is the real part of the amplitude, the imaginary part. So you have all these poles. But then the reality is that when you go to real continuum, you shouldn't have those things. You really have like smooth things. You only have a branch cut. Okay. But then the physics is that indeed you're trying to approach it, right? You're trying to get it by having all these poles lined up together. Okay. But the problem is you never get it. You can't get a smooth functions on the response or the response function on the real axis. That's why people typically do is that they get a bunch of delta functions and then add an imaginary part to smear it out so that they can compare to experiment. But that's ad hoc procedure. So, but then what I learned from this project is this, right? You already have results converged in this part, as I mentioned. You can do finite matrix calculation to converge this calculation. When the energy is complex, the question is how do you extrapolate while getting around with putting poles on the real axis. And it turns out, if you do it the correct way, in the subspace, the Hamiltonian becomes non-Hermitian. Even though in your training calculation, your Hamiltonian can be perfectly Hermitian using harmonic databases or whatever basis you have. So it turns out these are the poles or the eigenvalues of the subspace Hamiltonian. These are also the poles of the rational approximations. And you notice that there's different type of poles. So there's this resonance poles. Okay, the cross is a direct calculation. The other one is come from the low subspace spectrum. And then there's a bunch of poles here. Okay, they line up like a branch cut, but then the branch cut is moved away. Okay, so then when you do the calculations with subspace eigenvalues, your response function is perfectly smooth on the real axis. If you have a resonance, you will have a resonant peak there. So you don't have those delta functions. Okay. So this turns out it's very similar to the other so-called non-Hermitian quantum mechanics method. So like this one, they basically have to design a single particle basis, okay, and then use a direct product, for example, to get a many-body basis and get this non-Hermitian Hamiltonian, which is high dimensions. And this is the eigenstates or eigenvalues they get. Right? You see there is a resonance value, there's a resonance eigenstate, eigenenergies, and then there's these lines, which is also like a rotated branch, and then discretized. So this is a three-body. This system you have poles like the bound states, and they have two branch cuts, and these are two branch lines. The branch cut actually merge one line, roughly speaking. Okay, so the response function you can get is smooth here, and trying to get down to the point here. This is the threshold of the branching point. So what is really intriguing or weird is that the small matrix model is trained by a large Hermitian matrix. But then if you use a large Hermitian matrix to extrapolate directly to real axis or to evaluate on the real axis, that result is actually worse than a small non-Hermitian matrix. You get it? So the problem is this, right? So as I said, if you do like high dimension calculations, you get a lot of poles there. But then your emulator is trained here. It's a low dimension, but it's non-Hermitian. When you extrapolate it, it's smooth here. So you trained it, and the emulator actually is better than the high fidelity calculations. So it turns out this. So I was talking about this linear algebra problem, right? But if you're in the end, if you think about that functions or your amplitude as function of energy, it's basically a summation of poles. And it turns out in mass, so this, with him and the other collaborators, during pandemic, they were just playing with all kinds of weird functions and think about the rational approximation. So this is like, think about this as a complex plane, and then there's a function defined in this complex plane, and then there's a branching point. Okay, so they have a particular algorithm you can think about as a data-driven emulators, and it just came out like this way. All these pole locations like that, because they're conjectured. Actually, there's the scaling law, how they are approaching the branching point. So this is the novel thing is that, yes, you can actually align the pole position first, and then we'll do the fitting when we do extrapolations. What's left over is the fitting, figuring out the residues. It's actually become a linear problem. And it's very general that it doesn't really matter what functions is, the location of these guys can be pre-assigned. Okay, they will have similar performance. And the thing is that if you know where the branching point is, you'll know how to assign those poles. And this actually comes back to this Hamiltonian, because in our response functions, right, the pole is really defined by Hamiltonian. But then the response function really depends on Hamiltonian and then the transition operators, how you excite the nucleus. And that defines the detail of the function itself. But then pole location is really determined by Hamiltonian. That's why it's kind of consistent with the observation that the poles here are not really sensitive to the details of the function itself. It just knows your branching point. Okay. Why do I bring this up? Because we're talking to Dean and other people who are interested in this. There's a lot of situations like this that you can access these functions in part of the complex plane. And you want to extrapolate to somewhere else. What is the nice extrapolate? And I think this might be helpful. Okay. And the other thing is that about PMN. So we talk about PMN, small matrix, and all those, but I think it hasn't been really addressed at this kind of issues. I would like to see that just look at one variable, how this kind of pole assignment can come out from PMN. That would be interesting. Okay. So the last thing I want to say is that still coming back to this complex energy stuff, you can perform calculations, solve these equations at complex energies. And so this is basically can be performed. I think this paper basically demonstrates that this equation can be solved using NQS. Okay, and this is the for photo disintegration or sections is related to the response functions, and we'll do the complex energy calculations. There are different ways to extrapolations. Right, these two actually establish results. This is what people call the LEAT and maximum entropy. I think Ali worked on before, so we haven't really used the emulator yet. Okay, these are details of the reaction, the neural network. I think I will just skip it. Now, I want to emphasize. So this complex energy idea is not new. People use it. Right? For the integral transformation, I think our problem master people here and use it, and then in the field body community, people have this called complex energies method. And what I want to say is that if you want to emulate those calculations, basically the work I have done show how to do it. Okay, I won't spend time on details how to do it, but the paper basically demonstrates how to do that emulations. Now, the other thing I want to emphasize is traditionally LEAT has been focused on the response function. And here I want to show, okay, it actually goes beyond that. You can do scattering amplitudes, all kinds of different things. So this is actually the emulation error about emulate T matrix. So it's really about nuclear, the particle diamond scattering amplitudes using this complex energy method. So this is error for different dimer binding energy, right? So of course, in the future, we can also think about emulation for both these type of calculations in the NQS or any other framework. The other thing is, since Jan mentioned the excited states, I want to mention that here, right? You already see these are three-body problem, and there's like a two bound state there. So even though you use complex energy calculations, solving inhomogeneous Schrodinger equation, you actually can get those states, at least for this toy model system. But I think the idea is the same as Jan's idea. We're trying to find a subspace. And here the subspace is really using like a Krylov rational method, apply this resolvent on that, which is expensive. So these are the stuff I showed last time, last meeting, but I haven't really had a chance to move it beyond that. Now, the summary. The ND is toward the finishing line, and basically NQS can be used for continuum physics in principle, and the paper demonstrated. And I think it really opens up a lot of opportunities. Now, so the other two things is this. So we talked about PMN, and we talked about reduced basis method. I think Patrick had this theoretic analysis about their connections. Right? But practically speaking, we as collaborations, we tell people how to use them, but they actually have complementarity, or you just say, okay, you do PMN, that's the best, don't forget about RPM, whether there's any complementarity between them. So I would like to have some discussion about that, because people will be confused. And of course, the other thing I already mentioned, whether there's a PMN for the rational approximation, but actually it's go beyond that. Because the rational approximation is about one variables, but PMN is about can be as many as possible. So this means, yeah, PMN can help generate the traditional rational approximation to the multiple variables that we interesting. Yeah, that's all.
Thank you, Sheila, for the nice talk and also starting some of the discussions. So are there questions for Sheila?
If we go back to the rational Krylov subspace slide.
If you move it, I cannot move. Yeah, now I can move it anymore. For some reason.
Where are keys were you know?
Big eye. I did. Think it was where?
Just 87.
Yeah.
Yeah. Is that the
Yeah, so perhaps you mentioned that, but how do you choose those sigma values?
how do you choose?
The sigma 1, 2, 7. The sigmas in the
Yeah, the details might be in the papers here, right? So basically what I did is think about sigmas as complex values. But maybe in some existing method, actually sigma is a real numbers.
okay, like is there a
So you can see what I'm doing, right? So it's actually enhanced. If you want to go to a particular state and you choose the right sigma, it's actually going to enhance that particular state in the basis.
I've seen these referred to as shift invert methods. Is that okay?
Yeah. So, but what I want to say here, right? So it turns out for the continuum physics, meaning that typically this is about, like people do this because for large matrix, but then they don't have continuum, they don't have continuous eigenvalues. But if we will get a continuum problem, that's going to get interesting. Yeah.
Questions for you? Yeah.
Maybe I'm a little bit intrigued by the fact that you said that the reduced matrix is actually better than the full matrix.
Yeah.
And I think the reason is that if you use the full matrix on the real axis, then you're really your accuracy is really limited by the finite basis that you use. Like if you're using a harmonic oscillator basis or whatever basis, you're not getting the continuum.
Yeah.
Okay. But then if instead you're doing the actual many-body techniques work very well far away from the real plane, right? Because it's bound. Then if you map your Hamiltonian there, then when you extrapolate, you're getting closer to the real physics than to the actual many-body calculation.
Yeah, so actually maybe it's related to symmetry breaking. So when you make Hermitian, when you make matrix non-Hermitian, it breaks the time reversal symmetry. I think it makes physics actually better. But from mathematician people know, if you want to use a pole or rational approximation to approximate response functions, and it's kind of really bad idea to put the branch cut on real axis. The mathematician knows it, but the issue is how do you put them away? How do you rotate it? Right? So this is those non-Hermitian quantum mechanics really about trying to move that. So if you move the branch cut really deep, so then the resonance pole will show up like at the same Riemann shape as a bound state. So it has to be your spectrum. It has to be your eigenstate.
See if I can construct a question, but I did not fully understand how quantum states were states. You do a variational Monte Carlo calculation to.
Oh yes, so yeah, it's a little bit general than that, right? So it's trying to solve that inhomogeneous Schrodinger equations. So using Alice, the way of thinking is like just make sure the left and the right, the states are aligned together. So the loss function is built in that way.
Oh.
So the left and the right vectors are aligned together. The angle between them approaching 0.
You have the cost function somewhere? Maybe I forgot.
We made the paper.
The response, you mean?
Related to
Yeah,
the
she's asking about the loss function.
For the response function, right? For the whole integration, you mean, or for this exact integration that we did?
So you have this, right? Right, so let me say this. So you define this as left.
Yeah, you
this as
maximize the
right.
fidelity between left and right.
Yeah, you basically just left and right. If you normalize it to 1. Yeah.
Okay, sense. Oh, just maximize the other one. But it's expensive because you need to compute the derivative of the local energy. So, yeah, we go beyond log 16.
No, can you do the same with the corner variational principle? If you minimize the, I don't remember the exact formula. I'm talking about continuum states. No.
Yeah, I'll ask Ali. I mean, in principle, you can come up different trial wave function. It's correct asymptotics, and then put in a variation approach. Yeah, I think it's doable. It's like hyperspherical harmonics. They try to use some way to construct internal wave functions. I think asymptotic is parameterized. Yeah.
Get the
Questions?
Now, let's thank Xilin once again. So at this point, we have a discussion session. So let me actually perhaps stop the recording so people